Hello everyone, I'm Harshita and welcome to this tutorial. And in this tutorial, I'll be demonstrating how we can formulate a cybersecurity problem as a quantum optimization problem and then implement using the block platform. Every second, enterprise networks process an enormous volume of traffic, and these interactions may include the HTTP requests, API calls, database queries, or the port scanning, brute force login, malware delivery, POS or DDoS. But uh, most of the events are perfectly legitimate, as I've characterized it here. However, they are mixed in with the malicious activities. And also to note, each interaction generates what we call a network event. So the challenge is that the security systems must examine whether these events are malicious or legitimate, and these events has to be examined continuously and then has to be decided as of how they should be handled. So most organizations have already deployed intrusion detection systems or IDS, which IDS, which analyzes the incoming traffic and also helps identify suspicious activity. But detecting suspicious traffic is only the first step. What happens next is the real challenge. Like, should the suspicious traffic be allowed to continue to the production service, or it should be redirected to a honeypot? So, unlike traditional security systems, which simply allows or blocks the traffic, this approach would give the defenders an opportunity to observe the attackers just while protecting the critical their own production server, which has got some critical infrastructure. So traditionally, these traffic passes through a firewall first and then an IDS, and then based on some predefined rules or ML models, the traffic is either blocked or allowed. So this simple decision introduces to two common problems. One is a false positive, which is where the legitimate users gets blocked, and the false negatives where the attacker gets through. And of course, both outcomes have their serious consequences. So this motivates the use of honeypot as an additional defensive mechanism. And introducing the honeypot here, it is essentially just a decoy system that looks like a real service. So instead of blocking the suspicious users, we redirect them to the honeypot, and this allows the security analysts to observe attacker behavior, capture malware, understand attack strategies, and also strengthen future defenses. So the objective becomes determining which traffic should continue to production and which should be redirected to the honeypot. So here, now let's just consider a simplified example consisting of 10 suspicious network events. As block currently supports only 10 binary variables, we have considered only 10 events. So when we are considering of events, we have to take into consideration that each event must be assigned to either the production or the honeypot, as I already told what an event is. And this is a binary optimization problem. So when dealing with binary optimization problems, we first have to declare the binary decision variables. So if each event is assigned to a binary decision variable, if xi is equal to 0, then the event is routed to the production server, and if xi is equal to 1, the event is redirected to the honeypot. So now our task is to determine the optimal assignment of these all the 10 variables. Uh, to see or to get a more mathematical representation, we first represent this network event as a graph, and each network event becomes a node. So next, we connect the related events using these weighted edges. So the relationship, these weighted edges may either arise as a relationship because of two events originating either from the same IP address or belonging to the same user session, or occurring close together in time. And sometimes they may also exhibit similar behavior. So the edge weight basically measures the strength of this relationship. So it's more like stronger relationship would receive a larger weight, as we want the optimization algorithm to pay more attention to them, and the ones with lower weights would often be ignored by the optimization algorithm. So once this graph is constructed, this cybersecurity problem has now become a graph partitioning problem. And this graph is exactly the input to the max cut formulation, which we will be seeing on the next slide. So now, this max cut formulation is just a mathematical way to determine if two connected events would lie in the same partition or in different partitions. Now, for example, if we consider just two connected nodes, xi and xj, and we want an expression that evaluates to 0 if both the nodes are assigned to the same partition, and 1 if they belong to a different partition. So basically this but instead of taking 1, now I'm assigning a weight to it, which is this wij, and then we see that the expression would look something like this. And now this expression acts as an indicator to whether an edge is cut or not. And to account for the importance of each relationship, we multiply this expression by the corresponding edge weight, as I told before. So the goal is maximizing this objective, and then see that this identifies a partition that maximizes the total weight of the cut edges. So block source optimization problems, which are expressed as QBOs, and they are minimization problems, of course. So then we minimize the negative of the max cut objective, and then after collecting, so expanding each term with that weighted edge, it would give us some linear terms which involve the individual variables and also the quadratic terms. When I mean the quadratic terms, I mean these terms like xi, xj. So after collecting these terms, we would obtain the standard cubo form, and this is what the final cost function would do. Although the original work considers larger datasets, our proof of concept contains 10 events because of the current platform limitations, and the link to the original paper is given in the description. So even though the instance is smaller, every step remains identical to the original methodology performed. So we will still construct the graph, formulate this max cut problem, and then derive the QBO. So once the QBO has been formulated, we would optimize it using the QAOA, and this is the actual workflow. These are the list of 10 events which have considered here. Now let's summarize everything we have done and also the stuff which we'll be doing in the future. So first we began with the raw network traffic. The idea is then extracts the suspicious network events. Then these events are represented as nodes in a weighted graph. This graph partitioning problem is then formulated as a max cut optimization problem, and later the max cut formulation is converted into a cubo cost function. So now, as we pass on this cubo cost function, we will see that the QAOA algorithm would optimize this cubo on block to determine the optimal traffic partition. So here, on a summarizing note, we have actually transformed the cybersecurity routing problem into a quantum optimization problem. Now that we have developed the mathematical formulation, let's move to the block platform. There we'll be constructing this QBO corresponding to a 10 event graph, and then execute the QAOA algorithm, and then obtain the optimal bit string. So finally, we'll interpret this bit string to determine which network events should be remaining in the production and the ones which will get redirected to the honeypot. We first need to define the relationship between the events which we have defined before. So now here I have a table which lists the 8 weighted edges in an example graph. And as we see, each edge represents a meaningful relationship, like two events originating from the same attacking IP address, or brute force login sequence, or any consecutive stages of an attack chain. So the assigned weights here reflects the strength of these relationships. Higher the weights corresponds to stronger evidence that the events are related. And then the weighted edges are exactly what determines the coefficient in our max cut objective, which we saw, whose formulation we saw before. And so, so this is our ultimate cubo cost function here, the text in black. Here we have actually substituted the edge weights into the max cut objective. And then after collecting all these linears and quadratic terms, we construct this final Fibonacci function. So basically, this is everything which our platform on block needs. So let's just have a brief look on how QAOA is usually executed. So QAOA is a hybrid quantum classical optimization algorithm. First, the QB is converted into a cost Hamiltonian. Then the quantum computer prepares an equal superposition of all the possible solutions. And it later alternates between applying the cost Hamiltonian and then the mixer Hamiltonian. After measurement, a classical optimizer would update the parameters controlling all these operations. So this process gets repeated until the algorithm converges towards a low cost solution. So this is a conventional implementation. However, on block, you don't need to do this. You just have to select the algorithm and that the execution goes. So just a brief note on how block simplifies the whole process. So block almost automates the entire workflow. As users, we only need to provide the cubo cost function and then it automatically converts it into the appropriate cost Hamiltonian and constructs the QAOA circuit. Later, it optimizes the variational parameters and then executes the circuit by itself. Then samples the resulting bit strings at a later stage and returns the best solution. So this basically allows us to focus on modeling the optimization problem rather than actually implementing the quantum algorithm. So once the QBA has been formulated, block takes care of everything. This is the block platform, and yeah, these are the experiments which I have already did. And now we start with a new experiment, and I already entered this. So you have this two divisions where one deals with the machine learning problem and the other basically deals with the optimization problems. So now I've given, as it is an optimization problem, I've chosen optimization here and then honeypot partitioning. And the cost function I've already formulated here. So let me show how to add it. So first, the cubo which has been selected by default, here we have given 10 variables where basically each variable will represent an event as I've already shown. Now we have this cost function. So how it's basically formulated, defined here is that we just add it here and then you have x1. So if you're only defining x1 and then give a 1 here, so you define some coefficient to it. Like if I give 9 here, as you could see that 9x1 has been displayed here. So now if I want to add a weighted edge between x1 and x6, for example, I choose 6 here and I've given 9. And we don't need this right now as it's not part of our cost function. So this is the exact cost function which I showed before, and it has been all entered here. Save and continue. Now I've chosen the default as simulator. The algorithm QAOA has been chosen. Uh, uh, And there are various simulator methods on block, like the state vector method, density matrix, matrix product state, and then the stabilizer method. So first, I am choosing automatic just to let it adapt to the best simulator method. So yeah, let's run. The optimization experiment has been queued successfully. So it's here, it's running still. Mm, let's wait. The QAOA algorithm has now completed its optimization and returned this optimal, bit string for our cubo formulation, which is here. So we actually here each bit represents the each of the events which we define, and 0, as we already saw, it denotes the event being getting redirected to the production server, and 1 represents that of the honeypot. And here's a cost convergence graph. So basically, this example only illustrates the complete workflow of how a real world cybersecurity challenge can be modeled as a graph first and then be converted to its max cut formulation, and then the QPU construction, and finally the quantum optimization using QAOA and how it's being implemented on the block platform. So here we didn't do anything. We just have to enter the cost function, and yeah, block takes care of everything, literally. So thank you for watching. I hope this tutorial has provided a clear understanding of how quantum optimization techniques can be applied to practical cybersecurity applications. Thank you.